So let's talk about nonlinear plans. To make life easy, I have chosen this plant, cart pole problem, and we will work it out, right? Then you will see what it means to say a nonlinear plan, and more than that, how we deal with nonlinear plans, right? So the cart pole problem is what you see on screen. It's a small cart with wheels, and then there's a pendulum on the cart. The pendulum is actually 1 degree of freedom. It moves like that, but it cannot move, it cannot fall out of the screen or into the screen. That is not possible. It can only move this way on the plane of the screen. Okay. And you can see the angle theta, positive angle, and the direction of motion x and y. Right. You can see all these labels there, x and y, and this is the force. There is some sort of driving mechanism to drive the cart, right, back and forth. You can drive it, but when you drive it, you have to look at where the pole is. What is the theta? What is theta dot? Not only the position, but also velocity, right? And you are given the mass of the pendulum as simple m and the mass of the cart capital M, right? And the force you generate is F. Now, what is the control objective here? What do you want to do? The control problem here is that you want to stabilize the pendulum, right? Not letting it fall this way or that way. But in the same time, you want to move the cart to a desired position and stabilize it there. It's not stabilizing the pole at any point, right? But desired point. We have a desired position, 1 meter, 1.5, minus 0.5, whatever it is. Once you set that value, the control system will have to drive the cart without letting the pendulum to fall to that position and stabilize. Right? So that's a substantial challenge. Right? Let's see how we can do that. But before we move on, is the problem clear to everybody? The plant and the problem. Is everything clear up to now?
Yes, sir.
Yes, sir.
All right. Then our first task is to build the model of the plant, right? We have to build the mathematical model of the plant. So let's focus on that first. So this is our cart, right? And this is the pole and the pendulum. So we assume the pole to be zero weight. It doesn't have any mass or weight. Okay. So we have only two masses, the pendulum and the cart. Now, when the cart is moving horizontally, because of the friction, you get Bx dot. Bx dot. X is the distance. So you get velocity, x dot, and opposite direction you have the friction, so damping. And also you can see the pendulum is moving like that, rotary motion. There is damping there also based on the angular speed. So you can see it over here. Theta dot is the angular speed. It's falling this way, right? Pendulum is falling this way. So the or the other way, right? The friction works the other way, opposite direction. And it is Q theta dot. So Q is the viscous friction for rotary motion, and V is the viscous friction coefficient for the linear motion. So these two forces are opposing the respective motions, the rotary motion of the pendulum and the linear motion of the cart. And also at this configuration, we have the pendulum mass, simple M. It has its own weight working downwards. And also we have two vectors, E theta and E r. So this is the tangential direction, this is the radial direction vectors, two vectors. And through the pole, there's a tension, okay? There's a tension, capital T. This acts on the mass, right? And also acts on the car. It works in both directions. Sometimes you can see when this is swinging like that, right? There's a force outward. The mass is trying to fly away, but the pole is actually keeping it in position, pulling it down, right? So when it does that, there's a force reflected on the mass as well, the cart as well, right? So it works in both directions. Right. So our first equation is for the cart. Our first equation is for the cart in I direction. I is this way, horizontal direction. And we can write U, which is the driving force of the cart, minus T times sine theta. T is the force acting along the pole, right? Because when the mass is swinging, it tries to fly away. So this is like pulling force on the cart. So it works that way, T. But sine theta, because horizontal direction. And there's also friction, Bx dot, acting against the motion. Therefore, it is minus, which is equal to mass times acceleration, x double dot. Right? We are writing in I direction. So this is positive and these are negatives. That is the first equation for the cart along horizontal direction. We also can write the equation of motion for the pendulum, M, horizontally and vertically. Now let's first write the pendulum equation of motion horizontally, okay? The only force acting on the pendulum is T, like that, but you have to get the horizontal component, T sine theta. This is negative, this is positive. You can see that. That is the only force acting on the mass, which is equal to simple M times acceleration, which is AX, x direction of the pendulum, right? Horizontal acceleration, AX. Now, if you write down the equation of motion vertically for the pendulum, you will see again tension coming in, but it's acting vertically downward now. So it is minus T cos theta. In addition to that, its own weight is there, mg, which is also acting downward, minus mg, is equal to simple m times ay, which is the acceleration upwards. Okay. So we have two accelerations for ax and ay, which are the accelerations along x direction and y direction of the pendulum. Now, we also know the acceleration of the pendulum is equal to the acceleration of the cart. Whatever acceleration the cart has, right? Pendulum also assumes that acceleration, right? But in addition to that, any relative motion of the pendulum with respect to the cart are also there. So this is the equation for acceleration of the pendulum, right? Now, if you elaborate on that, you can say AC, the acceleration of the cart is moving horizontally, and it has only one direction, 1D motion. Acceleration is x double dot. So we can simply write x double dot I, because I is the direction of motion. X double dot I. Right, that is the acceleration of the cart. Plus this one, right? Tangential acceleration and radial acceleration. There are two components. Two components. How do we write that? So if you go back to this diagram, you can say the acceleration tangentially, right? And acceleration radially, these two directions. With respect to the cart are like this. L theta double dot, this is the tangential acceleration because of the angular acceleration, right? L theta double dot minus Q theta dot, because this is the friction force or torque, right? That will resist the motion, angular motion. Okay, can see it over here. When the pendulum is moving like that with angular acceleration theta double dot, right? You get L times theta double dot acceleration here, linear acceleration, and you get rid of Q times theta dot because of the friction. You write it like that. And this E theta tells you the direction. It's at an angle. What about the other acceleration, which is radially outward, right? So L theta dot square, this is the centrifugal force. And it's being pulled by the due to the tension of the pole, and it is working against ER. So if I show you back again, this is the direction, right? The T actually pulls it down this way, negative ER. Okay, so that's how you write that equation. We have to be very careful when you write down individual components, okay, and their direction, the vectors and all. So that is bit of a practice and discipline that you really require. And the next, what we do is, now we can't have E theta and ER also in the equation. We have already a lot of unknowns. We can't have more. So this E theta and ER we use only temporarily to indicate the directions, right? Now we want to get rid of that using I and J. So in this small diagram, you can see the relationship, how ER and E theta are related to I and J, right? So this is I, this is J, horizontal and vertical. And this is ER, E theta and ER. So it's pretty obvious, right? What is E theta? E theta in this direction is cos theta I, right? Cos theta I, then sine theta J, both are negative, like that, coming from this diagram. And same way, ER, this one, ER is, if you look at this direction, right? This direction, and this is angle theta. It is cos theta J minus sine theta I, like that. So we get rid of E theta and ER in this equation. So now you have I and J, right? In all of these elements, we will take I's and J's separately. if you combine all of the terms with I, you can say AX. This is the acceleration of the pendulum along x direction. All of the items, this one and this one, because it is with I here, and also this one. Okay, this is the horizontal acceleration of the pendulum. Once you simplify, it turns out to be like that. Equation number 4. And if you collect all the j terms, you get AY, the horizontal vertical acceleration, right? Like that, and that is equation number 5. Okay. Is everything clear up to now? How we got this acceleration, right? Now we gonna substitute equation number 4, which is AX, right, onto equation number 2. So let's go back. This is the equation number 2. We have AX here. We're gonna substitute for AX. When we do that, this is what we get. Just simply getting AX over here. That's it. We have equation number 6. All right. Next, we're going to substitute AY, equation number 5, right, onto equation number 3. If I go back, this is equation number 3. We have AY here. We replace AY and substitute that expression. When you do that, you get equation number 7. Now, already you can see that we have sines, cosines, theta dot square, right? This is nonlinear. This is nonlinear. Next, I have written equation number 6 and 7 again here on the new slide. Now, what we do is we combine 6 and 7 equations after multiplying 6 with cos theta and 7 with sine theta, so that you will get rid of this t thing. The tension of the pole is not required, right? We don't worry about that. We worry about the angles, the positions, angular speed, and the heart speed, right? We want to get rid of t, tension. So we multiply this with cos theta and this with sine theta and add them together. So once we do that, you get mg sine theta on the left hand side and you get right hand side like that. Okay. And some of these terms cancel out when you do that. Remember this minus m L theta dot square cos theta, and here plus m L theta dot square sine theta. When you do this one, those terms cancel out. Now, sorry about this equation. It's not very clear, but let me tell it to you. This is m. This is rearrangement m cos theta x double dot. You take it to the to one side, and then ml theta double dot. You keep it on the same side, and you get this one negative minus m q theta dot. You bring it to the other side, right? So that's what we have done here. So that is equation 8. Now, if you look at equation number 6 here, t sine theta, this one, we have an expression for t sine theta. So in the previous slide, the one before that, you have t sine theta over here also. Equation number 1, we haven't used it yet, right? So we can substitute for t sine theta on equation number 1. So when you do that, it becomes like that. I want you to go through all of these equations at home, right? After my explanations, you can do that yourself, right? And rearrange this into this format, equation number 9. Capital M plus simple M, x double dot, minus ml cos theta, theta double dot, u minus mq cos theta, theta dot, plus ml theta dot square sine theta, minus bx dot. That is equation number 9. All right. So you can see that on the left hand side we have x double dot theta double dot. Here also x double dot theta double dot. Now gradually this is taking shape, somewhat similar to state space, but not quite, right? Now what is x? X is the card position, and that is an important variable. What is x dot? Card velocity. That is also very important. And on the right hand side, if you see, you can see what? You can also see the rotary angular variables like theta double dot, very important. Right? Theta dot, very important. Theta, very important. So these are actually some form of state variables, right? So x dot, theta dot. Now, if you think like that, you will figure out that state variables are actually x dot and theta dot. So you should be able to figure that out. And because you can see theta double dot in these equations, highest derivative is double dot, theta double dot. Okay. So we have two sets, x and theta, and first derivative is dot, and the variable is theta or x. So it's pretty clear what we are having right now. So other than the system being completely nonlinear, we can at least figure out the state variable clearly. Now what we do is we subtract equation 8 times cos theta from 9. So look at that one. 8 times cos theta. We multiply this with cos theta and subtract from 9. So why we do that? We can get rid of this theta double dot. This is ml cos theta double dot. Here it is just ml theta double dot. You want to multiply this with cos theta, right, and subtract from 9. Then you get rid of this term over here. Right. So when you do that, this is the equation you get. Please check term by term and make sure what you have here is correct. Equation number 10, x double dot is equal to this equation. See how nonlinear it is. So this is how the cart accelerates. This is how the cart accelerates. Of course, it depends on you, the force given to the cart, but it also depends on the mass of the pendulum, the angle of the pendulum, the speed of the pendulum, speed of the cart at that moment. All of these variables are there. It's a bit complicated relationship, right? How the cart acceleration is determined. Okay, but the good thing is that you know this complicated relationship now, so that you can go to MATLAB and program it if you wish. Okay, right. So that is about x double dot. So This is the highest derivative of x. Now, if you know how to calculate this, you can actually update x dot, and then you can update x. You can update the position of the card. You can actually simulate the motion of the card, x dot, x double dot. Right? In control system, in state space, what is most important is that you have an equation for the highest derivative. If you have this simulatable equation, you can calculate the highest derivative, and all of the lower derivatives down to the variable itself, you can calculate and simulate. All right. Okay, now this is about x. What about theta? Again, you have two equations here, right? You have to combine 8 and 9, and this time you have to remove x double dot and keep theta double dot, right? So when you do that, to do that, you have to multiply 9 by m cos theta and 8 by capital M plus simple m, and then subtract. Okay. So when you do that, you get this equation, long equation. Please take it as a homework and make sure you get this theta double dot. So there you are. Now you have a complicated equation, nonlinear, but the good thing again is that you can program this equation and update theta double dot. Once you know acceleration of the angle, you can actually calculate the velocity, angular velocity, and the position, right, the angle itself. Then you can simulate the whole motion, not only the card, but also the pendulum in MATLAB. Now, the takeaway is equation 10 and 11 are the system equations, right? They tell us that they are all highly nonlinear. So this is, you cannot have this into a x dot equals x plus bu kind of thing. It's not linear, right? All the state space things that we have discussed, right, up to last week, right, are all linear state space models, right? A is a constant, so is B, and so on. Now this time you can't separate it like that. You have nonlinear equations. You have to deal with the equations as they are. Is everything clear up to now? Any questions, please? No questions? Is everything clear?
Yes, everything is clear.
All right. But by the way, I will upload this to the website. You download it and go through each and every equation and derive it yourself, okay? So to get a good practice. Now the problem is how to deal with nonlinear plans. Now again, we don't direct deal with nonlinear plans, but what we do is we convert the problem to our convenience, so that we can apply what we know. We know how to deal with linear plans, and the plant is nonlinear now. Why don't we convert it to a linear model? That's what we do. And when you do that, you have to be very careful. You can't just convert a nonlinear plant to a linear plant, right? You can't change the physics of the plant, right? Now we have to make assumptions. We have to restrict the operation so that the linear model will represent the nonlinear plant in that small state space, right? So we assume that the inverted pendulum, right, like that, or the pole card, will stay like that most of the time, right? It doesn't go like that or like that. the pole angle is not big. Pole angle is not big, right? We have some sort of control. We start vertically. We don't start like that, right? Let's say we start the operation somewhat vertical, not exactly, but somewhat, right? So an entire duration, it moves like that. Okay, if you want to move negative direction, it goes negative. Positive direction goes positive, and there's a little swing, not much. If you can maintain that status, right, you can assume these things. Theta approximately equal to 0. Theta dot is also approximately equal to 0. There's no big velocities, right? And in that case, sine theta equals theta, cos theta is equal to 1. And because theta dot is very small, theta dot square is even smaller. So with these assumptions, some of the variables in your equation, like theta dot, for example, this cos theta becomes 1, and sine theta becomes 0, and this sine theta also becomes 0. Sorry, sine theta is actually theta, but theta is very small, and theta square is even smaller. So this whole term is 0. And this is just theta. Sine theta equals theta. Right? When you do that, this is also 0 because sine theta is theta, but theta is small, and theta square is even smaller. So we'll set it to 0. This is the final equation, linearized equation for theta double dot. Now see, this is how you do the linearization. It's not just a mathematical process. You have to look at the physics and figure out and decide, okay, I'm going to keep the plant in that state, and it has to be a reasonable state. You can't have anything of your own which doesn't agree with the physics, right? Something like this. You can see it over here. These assumptions are actually reasonable assumptions, right? You can't have theta equals 45 degrees and theta dot equals 0. No, that is not reasonable, right? Physically, it is not acceptable. So it's not arbitrary numbers that you pick up for your convenience. You have to think about a reasonable, practically feasible state, and you put the numbers around that state and convert the nonlinear dynamics into linear dynamics, right? So this is, remember, this is linear. The moment pendulum swings like that, your model is not valid. The model is not valid. If you use this linearized equation for theta double dot, and when you simulate it, if the pendulum goes like that, you have to immediately stop the simulation because there's no point of seeing that result because it is not valid, right? You have to make sure that it stays vertical almost, right? Little swing is okay, but not too much. Now, you can now separate the variables on the right hand side. What do you have? Our main variable set is like 4. You have x, you have theta, x dot theta, right? So if you separate this the right hand side into the 4 variables, x, there's no x there, so it is 0x. X dot, yes, we have x dot here, minus b over ml. Do you have theta? Yes, we have theta. Do you have theta dot? Yes, we have theta dot. And in addition to that, we have u. This one. So you separate out into the state variable and just keep it there. Then let's take x double dot. That is this equation, right? This equation, equation 10. There are also same assumptions like sine theta equals theta, theta dot is approximately 0, like that, okay? So sine theta equals theta, cos theta equals 1, theta dot square is 0. This is the equation, linearized model. Again, if you separate the variables, there's no x, so 0x. What about x dot? Yes, we have b over capital N. And what about theta? Yes, we have theta. What about theta dot? No, we don't have theta dot. Right? Do you have u? Yeah, we have u also. Right. Now we have two equations, theta double dot and x double dot. Now they are all linear. Right? You can write down the linear state space model. There you are. Right? This is the linear state space model. X dot, theta dot. Okay. So when you write it down, on the left hand side, what you have is one derivative higher order. Okay. So when you have x, it is x dot here. When you have x dot, it is x double dot here. When you have theta here, it is theta dot here. When you have theta dot here, it is theta double dot. So in fact, the two equations we have here, theta double dot and x double dot, are here. Theta double dot, this one, and x double dot. If you look at the other two equations, x dot, what you see is nothing but the same equation. X dot equals x dot. And if you look at this equation, you see theta dot is equal to theta dot. So they are not independent equations. It is the relationship, right, in the state space model. You have seen this earlier also when you have number of state equations, right? The second state variable is the derivative of the first state variable, like that. Okay, you can see the fourth one here in this vector is equal to the third one over here, and the second one over here is equal to the first one over here, like that. And interestingly, u, the control input, goes into two equations here, second equation and the fourth equation. Right. So to develop this skill is quite a challenge. You need to spend some time going through the steps, each and every steps here, and then eventually come to this this state where you have the state space model, and it is a linear state space model because we have linearized. And remember, this linear state space model accurately represents the nearly vertical position of the pendulum. Okay, card position is not a problem, right? You can have any card position, but pendulum position, the pole position, has to be nearly 0. So you can identify system matrix A is this, drive matrix B is this, and symbol x dot equals x plus b, this format. Remember, this x is not the the position of the card, right? So you might confuse yourself, right? This direction x, this direction is y, right? This x. This is the dimension, horizontal dimension. But when you are in the state space model, all of the state variables are tagged together as x dot, right? I mean x, and x dot, x double dot, and so on, right? So sometimes these x represent x and x dot both if they come as a vector, right? So fortunately, in this particular case, this x represent actual x. This x dot represent actual velocity, okay? And this x double dot represent actual acceleration, fortunately. But in general, in state space, x means the entire vector, right? Here, we don't have to worry about it. The variables are as they appear here, okay? They're physically attached to the physical plant, x theta, x double dot, theta double dot, etc. Okay. Now you can see the output matrix y equals cx plus du, the second equation in the state space model. Now this time, what do you think? In a usual state space model, most of the plants we have worked up to now, we had only one output, one measurement, right? But here, we have two measurements. We are going to measure, of course, x, right? X, y. That is a requirement. We want to move the car to a certain distance and stabilize there. So therefore, we have to measure x. We have to measure x. So therefore, in the output equation, the matrix C here needs to have this row 1 0 0 0, so that when you multiply with the vector, state vector, you get x. Fine. There is another output that you have to measure. What is that? Can anybody guess what is the second state variable that you have to measure?
Yeah.
What's that?
The angle, theta.
Angle, yeah. Because, you have to keep an eye on the angle for a couple of reasons. Because if it falls down too much, right, you are in trouble. And the second thing is that we have already assumed theta is 0 or nearly 0. So if it goes too much, your assumption is not valid. So you have to keep an eye on that as well. So the C matrix has this format now. It has two rows. Remember the C matrix, the number of rows in the C matrix is the number of output measurements. If it is 2 outputs, it has 2 rows. If it is 3 outputs, it has 3 rows, and so on. All right. Now we have all the equations. Now we can simulate what happens when you run these equations, right? For that, we will go to MATLAB. Okay. So let's check the code. I have so many codes. That is carpend sim.m. So I want to go to part pen sim, this one. You can see the code here. I look at these parameters. This is the mass of the card, mass of the pendulum, length of the pole, and acceleration of gravity, etc. And also the two friction coefficients for linear motion and angular motion. They are also there. They are small, but you have to put that. Okay. Without that, the system will not be stable because you need friction to take the energy out so that motions are gradually diminishing and system converges, right? Do not simulate ideal things without any friction and all that, because you will easily make the system unstable, right? Always have some sort of damping in the system to take the energy out so that you can see something very realistic on your screen. Okay. What else do we have? Now we have this is x minimum, x maximum, y minimum, y maximum. This is for us to plot the graph, right? You can see it over here. This one graph axis, right? So then the time axis for the simulation, I'm going to simulate it for 3.5 seconds, 3.5 seconds with 0.01 sampling interval. And this is x0. Now this x is the entire state vector. It has x dot theta, theta dot. All right. So it is, I start with 0, 0, 0.5 and 0. What is that? This 0 is initial position, 0 position, okay? And this 0 is initial speed, and that is also 0. Initially, it is not moving anywhere, right? And this is 0.5. 0.5 radians for the angle. That is too much. That is too much. Okay. So I think I need to make it like 0.1 maybe, right? And this one is angular speed, right? That is 0, or else I can make it will give you a little value, 0.1. Initially, the pole is 0.1 radians off, and there's a little velocity also. What is this one? This is x ref. That is the reference x, where I want the pole to go and stabilize itself, right? That is 0.5. I want the pole to move 0.5 meters and stabilize there. And this is x dot. Do I need any velocity at the final point? No. Do I need any angle at the final point? No. Do I need any angular speed at the final point? No. So therefore, these are all zeros. I only want the card to move to 0.5 meter position and stabilize the whole thing there. Right. After that, what do I have? I have a linear state space model. The model be generated, and I want to simulate using linear state space model. There is no feedback control, anything, right? If I start like that, what's going to happen to the plant? What's going to happen to the plant? Right? I just want to simulate. So it will fall back and swing and all that. That's it. Okay, there's no control. That is the first thing. So for that, I don't think linear model is very valid, right? I need to use the actual nonlinear dynamics. Of course, even though I studied the linear SSM, inside that I have the nonlinear equations also. I'll show it to you, right? Because the pole falls like that. If you don't have any control, it falls. So therefore, your linear model will not represent the actual physics. Okay. And after that, we have two controllers here. We are not discussing them today, maybe next week. We have PPR, PP regulator. What is PP regulator? Can somebody figure that out? What is PP regulator? It is the pole placement regulator. Remember the state feedback? This is another word for state feedback. Either we finished state feedback control a week or two back. You can use state feedback control to stabilize the plant. And this is that controlled operation of the plant using pole placement regulator. And there's another controller, LQR, linear quadratic regulator. Okay, we're going to look at all these things next week, but today we're going to see the open loop simulation. What's going to happen to the pole and the cart? Okay, so in that case, we don't have this reference. Reference is required when you control the plant. Okay. So because we have three simulations, the open loop simulation and the two controlled simulation with the controller, we have three options here to select. Okay, so I have selected the first one. I have the equations to solve using ODE45 function in MATLAB. When you have differential equations, right, that you want to simulate, you can use ODE45, right? Card pen, this one. So I use the linear model for that, unfortunately. But later I'll show you the real nonlinear dynamics. Then rest is actually plotting the results. And finally, we have some sort of simulation, card pen animation. You can see the real animation. So let's run it. Okay, so you can see the pendulum is falling because there's no controller here. As it falls, it gains the speed and then it moves the other way and the cart moves in opposite direction, right? Because the reflected force from the pendulum, and it goes almost vertical but not quite there because the friction takes some energy out of the pendulum. It goes to the maximum point and then swings back. So it keeps on swinging back and forth, right? So when you code it and when you see this result, you know that probably your code is correct. Okay, it complies with what we experience, what we think it is, right? So it's very important that before you implement any controls, right, that you see the open loop simulation so that to verify your plant is correct, your plant model is correct, so that then you can go ahead and design the controller. There's no point of designing a controller when you don't have the correct plant dynamics, okay, in the first place. And you can see these very repetitive waveforms, very beautiful, right? It goes like that for X and X dot, position and velocity of the car, right? Blue one is the position, it goes back and forth like that. And the velocity goes this way. Very interesting. And also theta, if you look at blue is the theta angle and red is the angular speed, right? It goes like that. It goes like that. All right. So this tells us that what we have done is probably correct. And let me show you this Lindsay's code. When in MATLAB, I can call a function, right? Another MATLAB code, lin_ssa. I always write different codes and then combine them in the main function. Otherwise, the main function will be very cluttered, very difficult to read. So linsim is also over here somewhere, and this is linsim, right? You can see this is linsim, linear state space model, entire system A, B, C, D, and after that it runs the card pole, the state space model. It generates a state space model. So if you look at the MATLAB implementation, also you can learn quite a lot. You have the main MATLAB function, which is this one, where you have initial parameters, initial conditions and everything, and also some sort of plotting and all that. But in the middle, the real core simulation and all that is not here, somewhere else. So you have linsim code, which is over here, which tells the state space model, and then it connects, it generates a card pole by the name card pole, the state space model using this command, ss command, state space A, B, C, and D. Now this state space model by the name card pole, right, can be used by the animation. So which is what? If you go back to this one, at the end you see card pen animation, right? This is the real-time animation, and it uses the state space model. Can you see it here? Card pen any. This is that one. This is where you have the animation going on. Okay, right. So we have given a pose here for us to visually see the motion and all. So there are three codes here. The first one is the first one is, I don't remember the names again, right? You have the main MATLAB code which gives you the initial parameters, and then for the system dynamics, you go to another model, MATLAB code rather, and then it generates the state space model, and then you come back to the main code and call the animation, right? That's how it happens. Okay, right. So I think that's it for the day. Any questions, please? There's some activity in the chat. Can I share the MATLAB code via LMS? Well, I can, but I don't want to. I want you to write it with you. You saw the code. It's very simple, right? None of these codes go beyond the 100 lines, right? Why don't you do it yourself? You will never learn to use someone else's codes, right? Initially, it will be little difficult, but every line that you write, when you see the result on screen, you will encourage yourself, right? You will encourage yourself to do better. Without that foundation, you will never be an expert in simulation, particularly MATLAB, right? You have to do it by the hard way. Learn it yourself. It's not difficult. Okay. Any other questions, please? Right. In that case, we'll stop for the day, and I'll see you next week. Have a good evening.
Sir.